In computer graphics, we often have to take the integrals of unknown functions. For example, we might do this when anti-aliasing an image during rendering. Typically, we use Monte Carlo methods to do the integration, which estimate the integral through a series of point samples. To understand how our method works, let's assume we're trying to integrate the following 1D function. We can randomly sample the signal and evaluate the integral with the traditional Monte Carlo approach. The estimate of the integral is noisy and converges slowly as we take more samples. Another technique commonly used to increase the convergence rate is known as stratified sampling, where the function is divided into bins where only one sample is placed. This allows the integral to converge faster, but it still takes a long time to reach a stable result. Another common approach in computer graphics might involve fitting a parametric curve to the measured samples. However, these techniques rely on least squares methods, which require enough samples based on the highest frequency content of the signal in order to reconstruct them correctly. Once the correct sampling rate has been achieved, however, the integral converges to the right answer. Our approach is based on the novel theory of compressed sensing, which estimates the signal assuming that it's sparse in a transform domain. By doing so, we're able to approximate the original signal more accurately with less samples, leading to fast convergence of the integral. The details on how compressed sensing does this are in the paper. A comparison of the four approaches shows the accelerated convergence rate of our technique for this simple example. In this paper, we apply these ideas to two problems in computer graphics: image anti-aliasing and motion blur. First, let's examine the problem of image anti-aliasing. Our goal here is to band limit the high frequency content of a signal to reduce the jaggies that show up in the rendered image. We do this by applying a box filter integral to the continuous image signal underneath each pixel. Let's see how we do this with our compressed sensing approach. Suppose that we have a continuous scene signal which we want to anti-alias for rendering. Each square here represents a pixel in the final image. We want to integrate the scene function over the pixel to compute its final anti-alias color. We're going to evaluate this integral by taking a series of random point samples like we did before, but this time we're going to use compressed sensing to estimate the rest of the signal. Since our approach works on discrete signals, we first assume an underlying grid resolution for which we will solve the compressed sensing problem. We then use our ray tracing system to evaluate the scene function at random points in the image. Note that these samples are at the center of the grid points of the underlying grid. At this point, all we know about the scene is what we measured at these sample positions. We then approximate the values of all the remaining samples, assuming that the signal is sparse in the wavelet domain, using a compressed sensing algorithm known as regularized orthogonal matching pursuit, or ROMP. Once we have approximated the original scene, we downsample it to get our final result. Here we show an image at 256 by 256 resolution, which was anti-aliased with our algorithm. When we compare with the traditional stratified sampling approach, we see the improvement of our technique. We now look at our second application, the rendering of motion blur. In this case, we assume the scene is dynamic and integrate the projected image over the time that the aperture is open. To run our algorithm, we take the ray trace samples from a spatiotemporal volume, which represents the changing image over time. We then use the compressed sensing algorithm sparse to reconstruct the video volume, assuming that the final signal is sparse in the Fourier domain. Once we have solved for the full volume, we can integrate it over time to produce our motion blurred result. To see some results, we move the camera in the train scene to produce a motion blurred image. Here is the reference image rendered with 70 temporal random samples. If we take only one temporal random sample per pixel and reconstruct the image with traditional Monte Carlo, we get a noisy result. Our approach, on the other hand, reconstructs the full temporal volume for the motion blurred image, yielding a better result. Our algorithm can also be compared to state-of-the-art motion blur techniques. Here is the ground truth reference image of the pool ball scene. We now render it with the Hachisuka et al. Adaptive sampling algorithm of SIGGRAPH 2008. We see artifacts because of the reconstruction. We also show the results of rendering with Overbeck et al.'s adaptive wavelet algorithm of SIGGRAPH Asia 2009. This algorithm also results in artifacts. Our algorithm, on the other hand, reconstructs a much smoother motion blur because it has faithfully reconstructed the temporal volume of the moving scene. We note that comparisons like these put our algorithm at a disadvantage, because other algorithms are adaptive and do not have to place an equal number of samples at every pixel. Our algorithm, on the other hand, is much simpler and is actually non-adaptive. One interesting aspect of our technique is that it can easily be extended to the rendering of animated scenes. Since we evaluate the entire time volume to compute our motion blur, we can simply view the frames directly instead of integrating them together. This allows us to reconstruct a video stream from a sparse set of ray traced samples. Here we show the original video of the train scene, showing the camera moving over time. We now show the samples we evaluate with our ray tracer using a 25% sampling rate. The green colors represent unknown pixels. Note that the visible artifacts are due to the compression that was used to create this video, and are not present in the actual rendering. From these samples, we can reconstruct the following video stream using our approach. We see that it's quite close to the original video. If we try to reconstruct the video with other approaches, such as applying a linear reconstruction kernel, we do not get a good result. The application of the 2D compressive rendering approach that we proposed earlier in work published in TVCG also does not give a satisfactory result for this low sampling rate. The reason for the improvement of the new method is that we're now able to exploit coherence in the time dimension as well, because we reconstruct a full spatiotemporal volume. We can push the algorithm further by reducing the sampling rate considerably, even going down to a 1% sampling rate. Remarkably, despite so much missing information, we can still reconstruct a reasonable approximation of the original video using our approach.